So the sixth method of preparation from Grignard reagent. So Grignard reagent, I have discussed already reaction with nitriles. Now we'll go for esters, acid chlorides and other acid derivatives. So first I'll be taking an ester. So this is ester plus RMGX. What happens? R goes and attacks on this carbon atom containing the C double bond O group. Okay, this part leaves and you will get C2H5. R goes and attacks here. This part leaves with this, so C2H5O MgX plus you get H C double bond O R. So this is your aldehyde. Okay, from forming ester you will get your aldehyde. If you take some other ester, plus let me make this R dash MgX. So R dash goes, attacks here, you get RC double bond O R dash, which is your ketone, plus this particular group C2H5O having a negative charge forms this organometallic compound with magnesium. Similarly, if you take an acid chloride or acid anhydride, this acid chloride, you will get your corresponding aldehyde and ketone. So you have acid chloride with CH3 Mg, let's say Br, and okay, where X is halide, you know. What happened? CH3 goes and attacks here, so you will get CH3 C double bond O CH3, which is your acetone, plus you will get Cl Mg Br. Okay, here if it will be Cl, you will get Mg Cl, that is Mg Cl2. So that was basically what will happen with acid chlorides, esters and acid anhydrides. You get the corresponding aldehyde and ketone. Simple Grignard reagent reaction. The only disadvantage is that Grignard reagent cannot produce tertiary alcohol. You know that Grignard reagent can go all the way to give rise to our alcohol. So the aldehyde or ketone can be further reduced to alcohols. The ketone can be reduced to tertiary alcohol. That's the main problem in this reaction. So in order to stop at the ketone stage, use a weaker agent, okay, a weaker organometallic compound, which is, you can use Gilman's reagent, which is LiR2Cu, where R is the alkyl or alkenyl group, and the main reason why we use this LiR2Cu is that this will react faster with the ester and acid chloride than reacting with the aldehyde or ketone to give rise to further alcohols. Okay, so basically Grignard reagent will again react with the ketone plus RMGX. So this goes here, so it will give rise to the alcohol, tertiary alcohol, minus, and it will pick out proton to give tertiary alcohol. So that's the main problem of this reaction. So if you use a Gilman's reagent, it's LiR2Cu, it reacts faster with acid chlorides, acid anhydrides and esters. Therefore it gives mainly ketones because it doesn't react with ketone faster than those. Okay, so that's about this. Then the next I'll tell some important reactions. First is Rosenmann's reaction. Okay, seventh method, I will be taking only from acid chlorides. In Rosenmann's reaction, you have an acid chloride, CH3COO, you treat with hydrogen planes of palladium as the catalyst and BaSO4 and sulfur, and you will get your aldehyde. In Rosenmann's reaction, H2 by PD, and you treat with barium sulfate in presence of sulfur. These are the reagents and poison catalyst and all, and you will get only aldehyde as the product. Let me give you some other ways by which you will get. So if you have an acid chloride and you treat it either with lithium, aluminium hydride, tertiary butoxide, or SnC4H9 thrice H, you will get the product as an aldehyde. Okay, so if you take an acid chloride and you treat it with lithium ditertiary butoxy aluminium hydride, okay, lithium di 2 times third butoxy, this is butyl group, di third butoxy aluminium hydride, or if you treat with tri-N-butyl tin hydride, so this is 3 times tri, this is N-butyl tin hydride, tri-N-butyl tin hydride, or tertiary butoxide, lithium aluminium tertiary butoxide hydride, you will get, ditertiary butoxy hydride, you will get your aldehyde as the product. Okay, so that was from acid chlorides. And if I talk from esters, let me take an example. I'm purposefully writing in this form. You either treat it with dibal or NaAlH4, that is sodium aluminium hydride. You will get here CH3, CH2, it cleaves here, CHO plus OH, CH3. Okay, what happens? These are reducing agents. So NaLH4, this hydrogen, one hydrogen gets attached here, another gets attached here, cleavage across the ester linkage. So CH3, CH2, C double bond O, here you get a H, so this becomes an aldehyde and this becomes an alcohol. So your products will be aldehydes plus alcohols. So esters are converted to alcohols by either dimer or NaLH4. What is dimer? Diisobutyl aluminium hydride. Okay, so this is diisobutyl aluminium hydride. Diisobutyl aluminium hydride is dimer. Both of this will convert it to aldehydes. How to prepare ketones? You take your acid chlorides but in a larger quantity and you treat with dialkyl cadmium Okay, from acid chlorides, how will you get ketones? You take your acid chloride treated with dialkyl cadmium, you will get ketone plus cadmium chloride. Okay, so that was how to get ketones from acid chlorides, and you know how to get aldehydes. From esters you use diba or NaLH4, and you use Rosenmann's reaction for getting aldehydes from acid chloride. Okay, next is Stephen's reaction. Here use RCN. Depending upon your R, you will get the product. So RCN, you treat it with SnCl2 and HCl as the reagent. Remember Stephen's reaction, the reagent is SnCl2 HCl, and it undergoes partial reduction in the first step. So what happens if it gets reduced partially? So you'll RCH double bond NH. So this is a salt with HCl getting attached to this. So this is an aminochloride. Because this is an imine, this is HCl, so aminochloride salt. And then if you treat it with water, breaks here, you get RCHO plus here. So OH gets attached here, and Novel and H gets attached here, so you get NH4Cl. So Stephen's reaction, RCl, again nitriles, alkyl nitriles, SnCl2 HCl is the reagent. If you treat it, first is partial reduction taking place, H gets adding here, HCl because of nitrogen having that partial positive and a negative charge, this goes and attaches here. It forms a kind of salt because of the ionic pair attraction here. Then aminochloride salt is formed, treated with water, OH gets added here, H gets added here, you will get aldehyde plus NH4Cl as the salt. What happens? So first protonation, so RC111NH plus, I am taking its resonance structure, that is RC double bond NH, positive charge on the carbon, becoming more stable resonance structure. This is, you treat it Cl minus, then you have RCCl NH, and then if you treat it SnCl2 followed by HCl, you get RCH double bond NH, and if you do steam distillation, you have to do steam distillation, then you get your aldehyde. Okay, this was a brief mechanism. So RCN, protonation in the acidic medium, you get this compound, resonance structure, this one being more stable, positive charge on carbon, not treated with Cl minus, it gets attached here, SnCl2 HCl reducing agent, H here, so Cl goes, and then steam distillation RCl. Let's do a small example on this topic. So Cn, if you treat it SnCl2, HCl, water, and then heat, this is step 1, this is step 2, then you will get your benzaldehyde plus NH4Cl. Suppose if you take this compound and do it with same reagents, then you will get okay. So that was about Stephen's reaction. Now, you know oxo process, revision from alkenes. So I am taking an alkene. Reagent is carbon monoxide and hydrogen. So this is carbonylation or hydroformylation. Carbonylation and hydroformylation, and the catalyst is what? Cobalt, CO2, CO8. So write it in this way. Okay. Dicobyl octacarbonyl is the catalyst. So alkene with CO in presence of hydrogen with cobalt, dicobalt octacarbonyl as the catalyst. 100 degrees Celsius pressure, you get a mixture of aldehydes. Terminal aldehydes are always the major product in this reaction, whereas non-terminals are the minor product. What about Walker process? Let me take ethene. Okay, these are basically from alkenes we are studying. Plus PdCl2, it is palladium chloride in presence of water. This is my catalyst, and I use CuCl2 as co-catalyst in the presence of air or oxygen. You will get aldehyde plus palladium plus HCl. Okay, instead of this, if you use CH3 CH double bond CH2, you'll get ketone instead of an aldehyde. I hope it's clear. Here, if you use a CH3 group is attached to this, then you will get a ketone, otherwise it's an aldehyde with palladium chloride CuCl2 as the co-catalyst. You get aldehyde, gets back your palladium. So this is the kind of reaction from alkenes. From this is periodate oxidation. Periodate oxidation. Diols treated with periodate HiO4 or lead tetraacetate. So you will get RC11O R double prime plus RC11O R prime. Next, Swan oxidation. Swan oxidation. Primary halide, you treat with DMSO, that is nothing but dimethyl sulfoxide. You get RCHO. Primary halide gives you aldehyde plus dimethyl sulfide plus HX. Instead of primary, if you use the secondary, you will get a ketone. But if you use a tertiary, there will be no reaction. Okay, so Swan oxidation, remember with DMSO, you will get an aldehyde if you use primary, secondary ketone, and if you use a tertiary, no reaction. Instead of DMSO, if you use urotropin, which is CH2 6 times and 4, it's called somalate oxidation, and the products are similar. So, that was basically the brief methods. Probably one of the last ones is Neph carbonyl synthesis. Neph carbonyl synthesis. So this is from nitroalkanes. The necessary condition, the nitroalkane should have at least one alpha hydrogen atom. The nitroalkane should have at least one hydrogen atom, and the reagent is concentrated NaOH, and then followed by 70% sulfuric acid. I mean 70% concentrated sulfuric acid. So R CH2 R and double bond O NO. So what is this? This is a nitroalkane, and if you treat with NaOH, what happens? It will undergo tautomerism in equilibrium. So R C and then if you treat with 70% H2SO4, you get R C double bond O R. Okay, so nitroalkane, at least one alpha hydrogen should be there. So one alpha hydrogen is there here, and then if you treat NaOH in basic medium, tautomerism, this and 70% H2SO4, you get your ketone. If you take RCH2 and double bond O and you do NaOH in the first step, the tautomerism takes place, and in the second step you treat with 70% sulfuric acid. So what will you get? You get R C double bond O H. So this is your ketone. In this step you get a ketone, and here you get an aldehyde. Right? So quite simple. Come to the last method. This is only for ketones. From acetoacetic ester by ketonic hydrolysis. You should know that acetoacetic ester will undergo acidic hydrolysis as well as ketonic hydrolysis. From acidic hydrolysis the products will be different, but going by ketonic hydrolysis, let's see what the products happen. So either you treat with acetoacetic ester or any of its acid derivatives is treated with an aqueous acid. dilute aqueous acid. So hydrolysis of acetic ester or any of its acid derivative in the presence of dilute aqueous acid, okay, which is the ketonic hydrolysis, will form ketones. So this hydrolysis, ketonic hydrolysis, there is different hydrolysis possible. So basically this is characterized by loss of an carbon dioxide. Let me write acetic ester. This is aceto. Okay. So this is acetic ester. Treated with water, you will get acetone. Acetone is the most commonly used ketone, plus carbon dioxide, because this is characterized by loss of carbon dioxide, plus what will you get? So what happens here? Cleavage occurs here and here, because remember, if you do by ketonic hydrolysis, that is dilute aqueous acid, you have loss of carbon dioxide. So if you want to remove carbon dioxide, this should be removed. If this is removed, this is the ketone which is formed, and here you will have the alcohol being formed, because this is plus delta, and when you form there, this CH3 gets added here, because this is plus delta here, minus delta here, so H gets added here and OH gets added here in the presence of water, and then you get dilute aqueous acid. When I tell any of its derivative, here CH can be replaced by CH3, then it will form an active methylene compound. Okay, so this is basically ketonic hydrolysis. Esters normally can undergo another kind of hydrolysis, giving acid plus alcohol. Hydrolysis over here, so this will give you an acid plus alcohol. That's different. Okay, that's not ketonic hydrolysis. So here you remember very dilute acid. Okay, now I'll briefly mention the names for preparation of aromatic carbonic compounds. I'll not go through the reactions because it's a kind of repetitions throughout the chapters. So I'll just tell you the names so that you remember. You know Gattermann, Koch formulation. Okay, here the reagents will be CO plus HCl. I'll give you a brief summary, I'll not go into the detail of this part. And here you have anhydrous ZnCl2 as the catalyst and Cu2Cl2 as the co-catalyst. Okay, so this was Gattermann-Koch formulation, CO plus HCl as the reagent, and your catalyst is anhydrous ZnCl2 and Cu2Cl2 is the co-catalyst. Have done a quite number of times in many chapters, so I am avoiding it. Then if you take toluene, if you treat it with CrO2Cl2 followed by water, you will get benzaldehyde. This particular reaction is called Itat's reaction. In Itat's reaction, you treat toluene with CrO2Cl2, but otherwise you can also treat with air in presence of MnO or CrO3 in the presence of acid anhydride and acetic acid. You will get back your benzaldehyde, but the Itat reaction is only treating toluene with CrO2Cl2. Then you can treat acid chlorides Or even let me talk about here, since we're talking about aromatic compound, let me talk about benzyl chloride, that is alkyl chlorides, with reagents. If you treat with either CuNO3 or CuNO3 twice with heat, or PbNO3, or if you treat with urotropine, that is CH2 6 times and 4, you'll get what you call benzaldehyde. So all these three basically will give you benzaldehyde or its alkyl derivative, depending upon the alkene and alkane or whatever that you take. Okay, whether you take an aromatic alkane, depending upon which position what all groups are there, you will get an aldehyde, which is a derivative of benzaldehyde basically. Then you know Gattermann formulation. Gattermann formulation, here you use Zn, actually use ZnCl2 plus HCN, but both rearrange and then you get a ZnCl2 plus HCl, and then you treat it with water and heat, you will again get your aldehydes. For ketones, use Hovenhouse reaction. That is, instead of HCN, use RCN in this case. So use RCN plus HCl and ZnCl2. Okay? Here you will be using HCN plus ZnCl2, which is nothing, which will form ZnCl2 plus HCl because of the stability. And in Hovenhouse you use RCN, so you get an ketone. Here you get just use HCl, so you get aldehyde. One more reaction, already taught in phenols chapter. This is from phenols. It's Riemann-Tiemann reaction. You will get salicylaldehyde. Similarly, you know how to do it from dry distillation of calcium salts. Suppose instead of format or all, we have something of this kind, then you will get the corresponding ketone. Okay, and if you use a mixture with format, calcium format, then you will get the aldehyde. It's the same thing. If you suppose benzyl chloride, so this is benzyl chloride, and if you hydrolyze, you will get what? CH, 2OH, 2OH on the same carbon atom, unstable, removal of water molecule, so you will get rise to benzaldehyde. Once more, here toluene, if you oxidize using V2O5 at 350 degrees Celsius, you will also get benzaldehyde. Or if you take styrene, and do ozonolysis, you will get again benzaldehyde. Grignard reagent, anyway you know what to do if I replace with aromatic compound. So this was a brief overview. I'll just discuss two good methods of preparation of aromatic compounds apart from this general method, and then I'll wind up with the methods of preparation of aldehydes and ketones. Wills-Meyer reaction, just for the sake of knowing. Not very much important, but if a trivial question is asked, you can answer. These are the reagents. POCl3 heat, CH3 twice NH. The presence of formic acid, this you'll get benzaldehyde. And next one is from benzene diazonium chloride. Okay, so this is an oxime. What oxime it is? It is formaldehyde, because it's a derivative of formic acid or formyl. See this HCOH is formic acid, remember, HCHO is formaldehyde. So oxime of formaldehyde. So this is basically, you take formaldehyde plus NH2OH, the removal of this water molecule, you get oxime, which is your formaldehyde. You know, formaldehyde with NH2OH, remove this, formaldehyde, treat with benzene diazonium salts. Diazonium salts being unstable, release N2, HCl is released with this H and Cl, plus you will get your benzoyl dioxide. Okay, this H goes with this Cl, remove the water molecule to form formaldehyde, that's different. This H goes up with this Cl. Once N2 is removed, so you have Cl minus, it picks up this H from here, this being goes and attacks this, and then you form this benzyl dioxide, and if you treat it with water, what happens? Tuck. So plus minus, so NH, 2H comes there, so you get your NH2OH plus C double bond O, that is your benzaldehyde. I hope it's clear. Leave here, OH gets attached here, so you'll have 2OH, so remove the water molecule, so you'll get the aldehyde here. You have NOH, H gets attached, so you have NH2OH. So that's the end of methods of preparation. Aldehydes and ketones, not much physical properties to boast at. So basically they are not very highly polar like your acids or alcohols, but they have slight dipole reaction, dipole polarity, slight polarity. But ketones are generally more polar because of their particular alignment, and in some cases they lead to intermolecular hydrogen bonding, not intramolecular if it's mixed with something. But enol forms are obviously more related to inter as well as intra, so it's more polar. But ketones, this is highly polar compound, even aldehydes. Okay, so this is the polarity, but apart from that they are not very much reactive and all, not very much soluble in non-organic compounds or inorganic solvents, much more soluble in organic solvents. Not much of physical properties to boast, but they are polar compounds. So if you talk of dipole moment, so this is basically physical property. This is 2.33 dB. LDH less polar, and this is 2.67 dB, and this is 2.88 dB, and you know all this from inductive effects and all. You know the inductive effect, polarity and all is clear, so let's not go into detail of this. So that's what all to talk about physical properties.